Good evening. Welcome to the 11th S.M.A.R.T lecture at CeMM. It's an experiment in the middle of the summer. We were not sure you would show up, and so we congratulate you, and we're very grateful. And we were discussing with Oskar Aszmann just a minute ago that perhaps the fact that it happens in the summer has a good feeling about the ability to think about the talk, because you're a little bit less bombarded with additional information. So I welcome you to a very particular S.M.A.R.T lecture that will hopefully stay in your memory for quite some time. So I see almost only individuals that know a lot about us, but just very, very briefly, you are at the Center for Molecular Medicine. It belongs to the Academy of Sciences. As you know, we are in this beautiful and historically important campus that grew from different sites in the 9th district to occupy this hill. And now that the Medical University is making new buildings, they're also revisiting a lot of the architecture, the past architecture, and there are beautiful books on the architecture of the buildings that were before the 1970 big towers that you know now. And so we are something that came late. We're built in 2010. And there are more or less 300 semis. More or less half of them are in this building, and the other half are part of so-called adjunct principal investigators that are mostly at the medical universities, but also at the University of Vienna and in other places. And we form a nice community, and most importantly, we have quite a lot of training. I won't read you the mission. I think that essentially what you can imagine is that we are really trying to identify scientific themes that can be translated into medically useful insights, by and large, at the molecular level. I'm not going to go into much detail. There are diseases that we're interested in. The diseases have very often, Ernesto Abela is smiling because he recognizes his own graph. He is sort of, we are trying to work on themes that impinge on several diseases. And so both inflammation, immunity, but also cell growth and cancer, as metabolism and aging, are really across many tissues and many diseases, and that is very important. And very briefly, of the principles, I mentioned them because they're relevant for this talk, at least the three last ones, which is the pushing opportunity into medical application, is part of one of our principles, but also empowering talents, and that is what we're doing here. We are giving students and postdocs the ability of listening to disciplines and cultural areas that they're not chewing every day. And very importantly, we're multiplied by sharing. We believe in sharing, and by sharing we mean communication and lectures and sharing data as soon as possible. So now let's talk about the S.M.A.R.T lecture. The S.M.A.R.T lecture, S.M.A.R.T stands for Science, Medicine, Art, Research, and Technology. It started, as I said, about 10 years ago. It's held irregularly a little bit because COVID destroyed all the regularities we were used to. And we really hope that it helps this community to think a little bit beyond what they're doing every day, even if, of course, we'd be very proud if we could call Oskar Aszmann part of our community. We are a little bit more molecular, and so we are very, very proud and happy that today we can become a little bit more holistic and a little bit more organismic and at the interface with a machine. I mention this because usually, and Professor Freismuth, who has been attending some of the earlier lectures, remembers we had a debate after. A debate means that there were experts that were sitting here, a student, a professor, and the speaker, and they were answering questions. Now we will just have a discussion. But the discussion only works if you will participate. So it doesn't matter if you're a lay person. We, meaning the CeMM community, are all lay persons in this sense. And it doesn't matter whether you think your question is trivial, it's philosophical, it's banal, it's a curiosity. Please ask questions, because we want to demonstrate that we don't need to organize a panel to have a lively discussions. And we have fantastic students that will run around like crazy bringing around the microphones. And we will tape this lecture for people who are not here. Very, very briefly, I'm not going to go through all the themes, but we had a number of lectures that covered a lot of ground, from the discovery of the alphabet as one of the biggest inventions in humanity, to how to build cities, or how to build a multi-billion chip company in the case of Hermann Hauser. But also, if you remember, some of you may remember the fact that we had Assyrian and Babylonian ability to read with differential equations almost the planet movements. We had Gian Domenico Borazio speak about palliative medicine and what to do to prepare for death. But very importantly, one of the two early lectures was Fabiola Giannotti, that is an astrophysicist that is the director of CERN, but also Norbert Bischofberger, who, as you know, is one of the most successful Austrian drug discoverers in history, as he was also the founder of Gilead and identified some very important. But let's now move to today's lecture. And it's a fantastic privilege to have Oskar Aszmann here. And I think at the very beginning, it is absolutely clear that one of the things that makes him special is that he loves the human body. He confessed as much to me just some minutes ago, and he remembers even that when he was a child, he was already interested in why do we have different shapes and forms, and everybody looks a little bit different, and he was sort of, let's say, curious about this and motivated to figure out what was behind it. He's a director of the Center of Bionic Extremity Reconstruction and the vice chair of the Department of Plastic, Reconstructive and Aesthetic Surgery at American University. He's also an EU board certified plastic and reconstructive surgeon with a focus on upper and lower extremity reconstruction, obviously, as you know already. He established the center already 10 years ago, and very importantly, he decided already many years ago to work together with the prosthetic company Ottobock. And Ottobock has become a showcase for how also an Austrian enterprise can become world leading in this subject. And that is very, very nice and inspirational to most of us. He founded departments, and I think that department is going to be more and more important. And actually, he's interested in all kinds of aspects that have to do with reconstructive surgery, both from the basic research point of view, and that brought him to a beautiful European Research Council grant, which, as you know, is one of the most prestigious grants you can get in terms of let's say, fundamental research in Europe, but also very deeply technical and very deeply clinical aspects. And I think that if one has to say what is, I'm not going to read you all the prizes he's won, because in the meantime, he's one of the few persons working in, well, one of the, I tend to exaggerate, but let's put it precisely. He is, in the medical field, one of the persons that has the planetary dimension. And that is not, it's not exaggerated. And that is not very common, because molecular biologists, there are many, but Oskar Aszmann, there is only one, at least for now, but there are more coming. Maybe for us, sort of the final thing to say about him is that the kind of research he's doing is giving us a glimpse of what being human is all about, what being human and not being human means, and also it shows us a glimpse of what the future may bring for humanity. And all of this is, of course, quite a love song to humanity and quite a love song to the human body. So, dear Oskar, thank you for coming and accepting in the middle of the summer this invitation. We're looking forward to your lecture. Thank you very much. Thank you.
Yeah, thank you for coming out to this special lecture. I'm amazed to see that the auditorium is full. at this middle of the summer day. Thank you, Giulio, for the nice introductory words. I have called my lecture Cyborgs Ahead, but the subtitle I think is even more important, meaning considering the value of the human body. Now, you need to know, as a plastic surgeon, we deal with patients from top to toe. We reconstruct defects from the scalp to the neck, to the extremities, abdomen, legs, whatever you have. And I said it to Giulio before, I think if there's any trade in the medical sciences or in the surgical field, I think it's plastic surgery that really values the human body as it is. He already said it. He didn't tell you the entire story. When I was a little boy, when 9 years old, I was sitting in a, what do you call it, when you're in a sauna, and I saw all the different bodies there, and I was amazed to see, you know, the skinny guys, the big guys, the very big guys. And I was fascinated by the variety of the human form. So the amazing thing is that because I am a reconstructive surgeon, in the end we get to places where you cannot move any longer in a biological sphere, but you have to move on to technological gadgets. And I think to gauge the border as to what we can reconstruct with biological means and what we can reconstruct with mechatronic means is also part of that lecture. So that the purpose of the questions this talk asks, this is kind of maybe surprising to you, is what is the essence of the body? What is an artifact, a tool, a machine? Can a man find a home in a machine? That is maybe a queer question, if you will, but there's many patients that come to our center and they say, oh, doctor, can you remove my normal arm and replace it with a mechatronic arm? Meaning that they have the expectation that part of their body will be replaced by metal and plastic, and they will still be and appreciated as part of their human body. The goal of this talk, I think, is that's what I want you to have when you leave these doors, is again the realization of the uniqueness of your own body that you have, to realize the inescapability of the body you have, and finally to realize the dystopia of transhumanism. And obviously any of these questions would be a long talk as itself. I have 111 slides, and I'm hoping I'm going to get to that in 45 minutes. So I start with this very funny slide saying from 1839, Theodor Schwann, I'm sure most of you in the audience will know him. The Nobel Prize was not in place back then, but you know that what was his big essence, what did he contribute to the sciences that we have? Anybody would consider that? It was, this is Theodor Schwann, this is the microscope. It was a 3-lens microscope that he used to do his science. And this is what he described, and this is his thesis, published in 1839. His teacher was Johannes Müller. Johannes Müller is one of the big anatomists of that time. Purkinje, Henle, all these names that you may know are all students and collaborators of Theodor Schwann. And so this is his contribution in 1839 in Berlin. And basically it says that whatever is, whether it's plant life or human life or any other life, is consisting out of cells. This was his main contribution. And so I think probably if the Nobel Prize were out, he would have won the Nobel Prize for that. And this is the simple scheme for that. And I think this is so we are all medical sciences. This is the most basic scientific image I can present for that. But I think it draws attention to one simple fact, and this is maybe here, is that an adult human being consists out of, would you guess, if you wouldn't have known, 10 to the power of 14 cells. That's a lot of cells collaborating to make you and me as a human body. And I think the even more amazing fact is that 70 billion, 70 Milliarden, 70 billion cells are dying every day and are being regenerated to make you and me as we live. So it means in the end that we are a constant cellular flow balance. Now just appreciate that for a moment. As you sit here, there is billions of cells dying and another billions of cells being regenerating to make you and me be as we are. Now, my graphic artist has made this funny scheme, and if you look here, so I started with one single cell some 57 years ago, and then I grew, and this is the adult state of being, and the human body that you see here today is basically physically present, but in 7 years, it is not the same cells, it's not the same molecules, it's not... This building, when was it built, Giulio?
10 years ago, more or less.
10 years ago. So if I would make a molecular analysis or I look at the concrete, it's still the same concrete that was there for 11 years ago. Now, if you look at my body in 11 years, I will be gone. Yeah, I'm dissolved, I'm not here. So this is me now with 56, and eventually I will be gone, you know, it will be dissolved. So the reason why I say this, you remember the subtitle of the talk was Considering the Value of the Human Body, Cyborgs Ahead. So we're talking about this consistency of the human being as it is. And I told you, what should you remember when you leave the door? You should have an appreciation for the body that you have today. So we will see where that goes. So what I'm saying is that in the end, if you lose a hand, so why do people come to us, to the plastic surgery department here at the University of Vienna? They come to us not because of no other reason, but because they have lost the hand or they've lost the leg. But just consider this, it's not just losing a leg, but it's also losing an irreversible loss of cellular potential and expression. Because the hand is not just a hand as a tool, meaning I can grab something or hold on to something, but it's also a way to express myself. Now, if you've ever seen a video of Glenn Gould playing the Goldberg variations, and if you've seen that video, you can almost start crying because you can see an old man in front of a piano, and he's expressing his entire intensity as a musician, of his soul, of his being, into these 10 fingers interacting with this piano. So what I'm trying to get to is that the hand or the foot or whatever we have in our human anatomy is an expression of ourselves as we are. So it's a loss of cellular potential and expression. I think that is an important point to make. So I'm getting further a bit, you know. So here we're going into the intrinsics of the hand. Now the hand has about 30 bones, tendons, nerves, and what have you. It weighs about 800 grams. So it's only about 1% of body weight. Now the amazing thing is that the hand, so the central nervous system is about 30% are just attributed to the connectivity of the hand. So if you lose a hand, you're losing cellular expression, you're losing part of your own body, but also you're losing the expression of a majority of what you can, how you interact with your environment. I think that's a very important point to say, that the hand as it is, with your feet, with your ears, with whatever part of your body, you cannot interact with the environment the way you do with these 10 fingers or with your hands. If you would think of your daily task, that I don't know, most of you I don't know here, but what would you do without your 10 fingers? So we have patients coming to our office and they say they've cut their pinky and life is horrible. I just came back from a trip, on a boat trip, and the sailor told me when he was 13 he lost the index finger and he was considering suicide. That's what he told me, because he lost the index finger. You know, it's crazy. But just because he said he lost part of his body and it's the index finger, it's so important to manipulate things. But just to draw attention to the fact that these hands are so important for us in regards to expressing ourselves, and this is the reason why much of our brain's activity is related to these 10 fingers. So this is a spinal cord. This is an image I've done myself in the United States back when doing my PhD there. This is a rat spinal cord, and what you see here are these cells, and these cells are related to hand movement. So if you would look at that, you would see here the motor neurons in the ventral horn of the spinal cord, and each single one of these is related to some function here. And one of the fathers of hand surgeries, Sir Sterling Bunnell, he already said that the hand actually starts where? It starts in the brain. So even though if you lose the hand and the hand's chopped off for whatever reason, if you have that neural network available, which most of us do, then we can reconnect that to whatever mechatronic device we have to make the hand work again. So this was my very first question when we started to do research in that, was how many axons actually go into the hand and arm, how many afferents, how many efferents. I thought it's going to be a click on PubMed. I thought I'm going to go to PubMed, I'm going to look it up, how many afferents. So there was no information of that. We're talking about, 7, 8 years ago. So I talked to one of my PhDs, and we looked it up, and then we finally found it out. So this is one of the historical, this is Robert Remak. He was a Jew working in Berlin. He wasn't able to get a professorship because of his heritage, and he had to go to Poland and to do his research there. And these are the first descriptions as to how many afferents and efferents are available to the human body. This was also around 1840. This is the only reference I could find about 10 years ago as to how many afferents and efferents are available in the human arm. And if you look at the title, it says it's a comparison between the axons on frog, mouse, dog, and man. And if you read the article, it talks about one human specimen. It's unheard of in today's world. You would think, it's maybe 10 specimens. It's one, silver staining. And if you look here, so this is C1, cervical 1, all the way to coccygeal 2. And this is the amount of motor neurons that he found, and this is the sensory neurons that he found. Now, when I was doing medical school and doing the cadaver dissections, you remember there's the rostral and the caudal tumescence. This is the widening of the spinal cord. And I always thought it's because, evidently, the motor neurons, because we have to think of how to move our fingers. But it's wrong. The motor neurons are basically consistently always the same, but it's the sensory neurons that multiply. So this is the C5, C6, C7. This is of our own lab.
You want me to turn on the
but it's a better picture coming here. It's the same, but it's just the cervical roots, and here we have this is the median nerve. Now, I think anybody here probably would know the median nerve. The median nerve is the nerve that goes through the hand, and it contributes these 3 fingers. These are the most important fingers, because with these, you touch. With these, you explore. With these, you read, and you do your thing. The median nerve, this is the median nerve at arm level here. Now, the green little dots are the motor fibers. The red ones are the sensory fibers, all around here. This one is the median nerve proper. This is the median nerve that's in your carpal tunnel. If you have a carpal tunnel syndrome, that's what's painful. It's stuck here. So here we have about 80,000 sensory fibers going from the hand to the brain. It's unbelievable. After I saw that, I thought to myself, this is really crazy. We don't have so many efferents, meaning nerves going out, but the majority of a peripheral nervous system anywhere in the body, not just the brachial plexus or the hand, but also the feet, is bringing information back to the brain. So I always say it's more important as a CEO, as a chief executive officer, to listen. Because if you don't listen and get afferents in, then you make the wrong directives. So it's always important to have more input than output. So this is the general scheme of things, so that we published in Nature. It's C5, 6, 8, 1, and we see the red bars are the preeminent, and so these are all the afferents. Meaning that the extremity, the upper extremity in particular, is able to listen. It's able to perceive, and whatever we think of Wahrnehmung or perception, it's perceiving, is percaptere. It's meaning we are feeling, but at the same time we are grabbing things. So it's the interaction of us interacting with our environment by perceiving things. I think that's a very important point to make. So the hand is primarily a sensory organ, an exploratory tool, an endoscope with visual capacity. Now, let me just say this. My wife asked me, and I says, well, can you look? And I say, let me just look. And I look into my pocket. Did I just say look? Yes, I look, because the hand is actually a tool with which I'm able to look. As a surgeon, many times we're in the body of a certain region where I cannot look. And I pull in my finger and I look to the ceiling and I'm exploring the internals of an organ. Is it not true? We do that very often. So the fingers have the capacity to look. So when we teach our children, we look with our eyes, not with our hands. Don't we say that to our kids? It's wrong. It is very important to have a look with our fingers, with our hands. We need to appreciate things with our fingers. The sense of touch is the most important sense that we have as human beings, because you cannot fool it. It's there. If you think of Thomas in the New Testament, you need to touch, We need to be in it. We need to be pervasive with the structures. So I'll show you a very funny image. Who would guess what that would be? Is that a 22-fingered human being? Is a polydactyly? Yeah, I heard it. Who is it? Yes, it is a star mole. It's called a star mole. For those who don't know what that is, it's an animal that lives underneath the earth. It's clueless. It has no eyes. It has eyes, but they don't see. And so this is the nostrils, and you'll see this is the animal. It has big fingers with which it makes holes in the ground, but it actually sees with what? With its eyes? No. It sees with its fingers around the snout. So this is how they perceive and they also hunt. They hunt their prey so they are braille readers, if you will. They decipher their environment with their fingers around the snout. So I say this because I get to this very important point. Now, if I would have given this lecture about maybe 7 or 8 years ago, I would have never in the world put that slide in. Movement, so we're getting into the prosthetics world now. Movement, so we're thinking of moving artificial arms, Movement is a sensory phenomenon. I'll show you a funny video. So this is a woman who had a lidocaine injected into a median nerve. You remember the median nerve? How many nerves went in there?
80,000.
80,000. Somebody remembered. So she's trying to light this, and it's very difficult to even pick up this thing, and it's even more difficult to light it because she also knows it's dangerous. And I'm showing this video because it draws attention to the fact that much of what we do, actually everything we do with our extremities, or even we talked about this in our research meeting today, the face. I'm just saying this in a moment, the facial musculature, if there's any neuroscientist among you, has no proprioceptive capacities. You can look it up. If Hans Lassmann would be here, he would nod his head. The facial musculature has no proprioceptive capacities. So that means that if we move the face, we feel it because of skin. We feel the skin deforming in our face. So the same for the fingers. Now, this is a very unique movie, and it shows you a human being that has perfect efferent abilities. All the muscles work, all the nerves work, everything works, but it has no afferent abilities. It's a congenital abnormality of the proprioceptive receptors. The patient cannot even make one step. He's determined to fall down. He cannot even sit. He has to crawl on all four. So just to point out the fact again, what I just said before, without afferents, all our efferent capacity is of no use. So I'll show you very funny movies. You will laugh about this. These are very complex mechatronic devices, very expensive, and they're trying to do very simple tasks like opening this door, and they're not able to, and they fail. And so I told you would laugh because it's ridiculous, really. It is ridiculous because it shows you how we would be if we would have not sensory capacities, meaning proprioceptive perception of ourself, self-perception. So this is where we go to my ERC grant. So I knew exactly, I thought, okay, so if I want to solve the problem of getting into the machine, I need to solve the problem of afferents. So this is the way we do that now, and this is one of the central images of our ERC grant. So we have a muscle, and we'll talk about this in a moment also. The muscle is a translator of neural information. Now, when you think you've lost the arm, and I told you, remember the slide of the spinal cord with the many motor neurons? How can I understand the language of the motor neurons? How would this be translatable in a meaningful way to drive a prosthetic device? I can't. So then we use the muscle as a translator for neural information. Meaning, let's just say the guy has lost the arm. I take a nerve, let's just say the median nerve, and I stick it into a muscle that is of no use there. And then the muscle will get this information and the patient will think of hand movement, and the muscle will start to twitch and translate neural information into meaningful EMG signals that I can then transmit to the device. At the same time, I'm transplanting a piece of skin, a dermal graft, onto the muscle to create an illusion of movement. At the same time, I can interact with that piece of skin to make the prosthetic device more meaningful. And we can translate this into a binary code that eventually the prosthesis will also understand. Now, it's important, maybe also at this slide, there is an impedance. And I say it's an impedance of complexity, because the language, the nerve and the muscle will speak will always be, so this is what we see here, will always be much more complex than the language that the prosthesis will understand. So there's a complexity impedance, and we're translating neural information into a simple binary code that eventually will be understood by a prosthetic device. So this is one of our early experiments, and we see that the nerve is growing into the muscle and beyond that through the skin graft into the skin graft. So we know that it is working. So these are animal experiments. We now have human experimentation where we know it works the same way. So this led to this article. 3 guys in Austria have become cyborgs after getting a robotic hand. And I think this is one of the reasons why our laboratory is so known around the world, as Giulio said, because we're dealing with human people, with human beings, translating what we have found in the laboratory into a clinical scenario. So these are our indications. So today is Monday, and we have visitors from abroad, and they came to visit us to see how we deal with these patients. Every other Monday, we see patients here at the Medical University of Vienna, and these is the patients we see. They are reconstruction of the limb loss, meaning an amputation, reconstruction of the massive neural loss, a plexus lesion, for example, reconstruction of the critical loss of functional tissues, an avulsion injury, or reconstruction after a central neural loss, like a brain stroke. I think we have seen everything today. Every single one of these we have appreciated today. These are the hands we see. And if you look very closely, this is a photo I'm very proud of, because it teaches you how we can reconstruct hands in the 21st century. 10 years ago, I couldn't have produced that image. Here we see the oldest hand transplantee in the world. He's an Austrian, you wouldn't believe it. It's Theo Kelz, you know him from the... So he is 21 years ago, he has received these 2 hands from a dead man, and it's still working. These are bionic reconstructions, and before we had to amputate this hand, we took one of his fingers and transplanted it as a single-digit transplantation to reconstruct the thumb on the other hand. And these are some type of bionic reconstructions that you can appreciate, and that's where we're going into that. So I told you at the very beginning of my talk that we're trying to draw the line between biology and machine. Now, I'm a firm believer in biological reconstruction. Don't get me wrong, I'm famous for bionic reconstructions, but I believe that biology is always the best. A fingertip alone has about 5,000 mechanoreceptors, and these mechanoreceptors can perceive to a degree that a little fly is sitting down and I can perceive that. That's tenths of a gram that I can perceive. Now, I do not know of a single engineer in the world who can produce a miniature mechanosensor and 5,000 of these within 1 square centimeter. It's impossible. And then even translating that into the machine is the next step we cannot do. So here we have a 7-year-old boy who has had an extensive sarcoma of the proximal humerus. And the chief of orthopedics called me and says, can we amputate the arm so we can get a prosthetic device on him? I said, let me have a look. So here's the boy. This is a bone cement, and the sarcoma resection had to sacrifice every single muscle in the arm, and it's just a soft tissue sleeve, and that's all that there is. But what you forget is that what happens under here? What's here? We don't see it even. What is it? It's a hand. Now, you remember what I said at the very beginning? How many % are related to hand function? 30%. So if I cut off the arm, his brain will go crazy. Suddenly there is a brain expecting a hand and the hand's gone. So we need to make every effort to save the hand. So here we have a bone from the leg. This is plastic surgery in the end. Yeah. So a bone from the leg, it's the fibula. And we have a bone from a dead man to augment the bone defect. And here he is after the first reconstruction, and then we do a bipolar pec major transfer, meaning the muscle from the chest, and we make a new biceps to save what? To save the hand. Because yes, he has a biceps, and here he's doing this, and you see him lifting the ball. Now, can that hand do better than a prosthetic hand? Now, no doubt. He has sensibility, his brain is connected to his fingers, he feels everything, he can take a shower, he can jump in the water. Now, no doubt that this is the best that could ever happen to the boy. When you think of a prosthetic device that replaces the arm, it's horrible, because he needs to attach a lot of plastic to the rest of the body. It's unbelievably sad. So this is the best option, even though it meant 3 surgeries, 3 risks and so forth. It's difficult for the parents, but for sure the best option for the boy. Here, a 45-year-old male with the 3rd recurrence of a chondrosarcoma. He will come and visit me in 3 weeks again here in Vienna. He's from the United States. He had a thoracoscapular amputation was the proposed treatment. And so here he is. We resected the entire arm. And if you have a close look, this is where the sarcoma is. It's in this chunk. And then I took the remaining arm. Why? Just to make him look funny? No, because it's the hand that's so important. So now he has a hand that's sensate, it's connected to his brain, it looks funny, but if he's in a business suit in front of you, you wouldn't notice the difference. He can hold his things, he can have sensation. His body image is complete, meaning that the brain that expects 2 hands has 2 hands. Now that is different if you would make a prosthetic device, he would never feel that as his home. So we think of the subtitle, can that be an alternative for us, the prosthetic device? And here we see him on the sideway. Now, if the patient has no arm, like this guy, he is a guy from Lower Austria, and he lost the arm, there's hardly anything left. It's just a piece of bone of the humerus. Now, what can we tell him? There is no hand there. It's an amputation. We need to do a bionic reconstruction. So what does that mean, in fact? So in this man, we have done a complex surgery. We have implanted a piece of steel, a titanium, into his humerus, and then we do nerve transfers. Nerve transfers means that we take the nerves that are responsible for the hand. You remember, the hand starts where? It starts in the brain. The brain's still there, the nerves are there, we reroute the nerves. You see there is the latissimus dorsi twitching. We do a surgery to reroute the nerves and then to avail the patient with a translator. The muscle translates the information to the machine, you remember? And so then so this is the implant. And here's coming through the bone, through the skin. And here's a short video. So he's driving this device with his own brain. He has an interface that is now directly covered from the skin. We're now working on systems that are wireless, connecting to the body. We'll see that in a moment. He has excellent control of his glenohumeral joint, and he can control his thumb and his fingers and the elbow extension flexion. So that's if you lose the entire arm. Yes, there is no question. We have to go to mechatronic alternatives. Or here, just to see that the patient can also, because he works in a farm up north, it's not just an academic result, but he can actually cut trees with it. Just to say that this is not something for the movie, but it's really for his helps. So it really helps him do his daily job. Bionic reconstruction, so we're moving down the axis. So we talked about now shoulder, now we're moving elbow. Transradial, here is a 13-year-old boy, again from abroad, and the sarcoma center in Birmingham, they said, we need to amputate the arm. Now, I think they have no clue what it means to sacrifice the hand of a young boy. So here, I'm sorry about these images, but I think it's important for you to see that. So this is the diseased segment of the arm. And so we are radical because we need to get rid of the tumor. So the tumor needs to go out. So we resect the tumor, and then we do a replantation of the arm to save the hand. So here he is, still under chemotherapy, 3 months after the intervention. If you would see the boy sitting here, would you notice anything's wrong with him? if you see him like that. The nurse tried to puncture his vein, and she said, "Why don't you bend your elbow?" He said, "I don't have an elbow," because she didn't realize that there was something happening here. So just to say that this is how he is, and these are the first, they're upside-down videos, but you can appreciate hand function. And these are the videos that his father sent to me from his home. Here he's climbing a wall. This video, before I started, he's jumping the rope. Now, jumping the rope is not so easy because you need to have proprioception when you jump the rope. Now, look at this guy. You could never do that with a prosthetic device. It will come off. You know, you don't feel the rope. You don't feel the thing. So here he is, and look at his face. He is really excited about that. I saw him. We have been in London recently for a research follow-up. He's now 18 years old. He's almost as tall as I am. He was crying for the fact that he has two hands, together with his mom. So I'm just saying, you know, it is important to think of biology first and then mechatronics second if necessary. So here we go to that. It's drawing the line, amputation versus bionic reconstruction. These are the patients we see most, probably about 30 a year. So we have tumor, trauma, contractures of all kinds, ischemia, plexus lesions. So these are patients' hands that I can show you here. Every single one of these hands has a story to tell, and I could tell you the stories. We don't have the time for that, but just to say that these hands are asensate, they don't feel anything, and they're without any movement. So here we have the concept now of how do we translate function into that hand. You remember I told you there is, I didn't say that actually, the entire brachial plexus, meaning the nerves coming out of the arm into the hands, is 350,000 nerves. It's a lot of nerve. But if you look at this, there is only 7,000 spinal motor neurons going into the forearm and the hand itself only has 2,000. Can you imagine? The hand itself that plays the flute, that plays the piano, that does surgery, that does all kinds of things, has only 2,000 motor neurons. I would have never thought that. When I was in medical school, I wouldn't have believed it. But now I know because we did that research ourselves. You can read it up. And it's only 2,000 motor neurons. That's it. And so if you look at this image carefully, if somebody has lost the hand, I have about 7,000 motor neurons that I need to account for. So when I reroute the ulnar nerve, now the ulnar nerve is the nerve that plays the flute, let's just say, or plays its intrinsic muscles. I can reroute the ulnar nerve that comes from C8 and TH1 and reroute it into a muscle that has no meaning in an amputation. And then that muscle will be a translator of neural information. And then I can pick up that information and transmit that into the machine with a binary code. That's important to say because the complexity impedance, I talked about that. So here we have, I call it the manunculus. You remember the homunculus in the brain? Now this is a manunculus. I think this is a funny word because it kind of tells you that we're creating a small hand in the amputation stump. So I think that's what the ERC committee liked. You know, it's very original. So we have a hand in the amputation stump. And so here we can have an interface with which we can communicate with a device. So this is basically what we're getting at. Now, what I need to say is that we have limited space. Limited space means that we have signals in a very small tissue available. So we need to go invasive. Now, since about 3 or 4 years, and there is my MDR specialist in the back, medical device regulations make us all crazy. I'm sure you all suffer from it. We too. And so we have, for example, here a device from a company in the United States. And with this, we can get into the muscle. And we have done here in our animal department with Bruno Podessa, we have done the first device, and we've published this just recently, going into the muscles after we have done the nerve transfers. You remember nerve transfers, lots of information in the muscle, the muscle being a translator. Now here we are basically implanting hearing aids. So we're planting sensors that can listen to what happens in the muscle, and it can get it out of the muscle into the machine. So this is a telemetric port, and here we see all this information coming out. And this is Clemens Stöttner, one of my PhDs, and he's picking up the information from the muscle as it goes into the machine then. So the idea basically is that we get all this huge amount of information that is being produced in the muscle and getting it into the machine. Now, this is an experiment that we have done just recently, a few weeks ago in London with our partners in Imperial College. And there's a guy with which we have implanted an implant very similar to this. And you see he's lost the arm. And you can see all these wires coming out. It gives you an idea how complex the information is that comes out. And so here we have him, and he's thinking of movement. The screen just turned off of the screensaver. But you would see all this information being picked up because he's thinking of hand movement, and all this information is going to be fed into this machine. It's a Bioelettronica. It's an Italian company, and so it's translated there. So the idea in the end is, and this is from the movie Avatar, basically to connect to the machine the way this guy connects to the animal, so we can have all this complex information being fed into the machine with a telemetry port. Here is a young man. He's a student in our laboratory. It's 8 electrodes mounted around the forearm. And look at the precision of hand movement that we can provide. Any hand surgeon, and I talk about this in the hand surgical communities, they are thinking it's unbelievable, the precision of hand movement that can be done today. It's a precision grip, collateral grip, power grip, pronation, supination, and all that really on command. It's unbelievable what these machines can do today. This is an Autobock product, by the way. And here is a guy, this was my very first elective amputation. And we have invested about 3 free flaps into his arm, so it's a lot of surgery. And then I said to him, he was an electrocutioner from Upper Austria. And I said, well, we can make an arthrodesis of the thumb and this. And he says, doctor, I'm 24. I spent the last 3 years in the hospital. I'm sick of having another surgery. But I heard there is an alternative. So I brought him into the office and I said, okay, so we mount the electrodes around the forearm. The hand doesn't do anything, but the nerves are still there. So look at him. He's now translating neural information to this virtual hand. I think he was crying when he saw that. After 3 years of having no movement in his own hand, and he says, I can move a hand. It's my own hand. It's basically my own, but I'm driving it. So we have said, okay, so I made a symposium. I invited theologians and doctors and specialists of all kinds. He was in Hörsaal 3 here in our university. And we have been discussing whether it is ethically feasible to amputate an arm to replace it with a mechatronic device. And so Ulrich Körtner, he was the theologian, he was there, he said, okay, we can do that. So we did it. So we have done an amputation. This was my very first amputation. My former chief, he was going crazy. He said, we cannot amputate a hand in my department. It was a big fight. But we proceed, and then this is 6, so this was the hand previously. This is about 6 weeks after the amputation. Now look at the quality of hand function. Very shortly after the amputation was done, it's a bimanual dexterity that is being, I think that was already at this point. And so we published it in the Lancet a few years later. And then we started to get more patients from different places, and we started to experiment in different ways. Now this was an electrocution injury that you've just seen. This patient we have reconstructed in the year 2001 after a brachial plexus injury. Back then, the boy was 14 years old. He borrowed the motorcycle from his father one day, and he crashed into a tree, and the plexus was out. Now, if you look here, this is the clavicle, the clavicular bone, and this is the data highway. You remember how many nerves come from the arm out? It's 350,000. So it's a data highway that is destructed. It's dead. And we see there's an avulsion of C8 and Th1. And anybody who knows, we've seen 2 patients today with that type of injury. It's very difficult to reconstruct. So this is his hand function. 15 years later, this is how he presents. He has no sensation. He has no movement, and he cannot pick up that piece of balsa holz. It's a little piece of wood. It's very light. So then I look at him. This is the rest of the patient, and it's a biologic wasteland from here downwards. So he can flex the elbow, but the hand here, and you can see it's already bluish here, and there's no movement at all here. But when I tapped the nerve here, he said, doctor, when you do this, I have something going on. So I knew some nerves have made it down into the arm. So then I proposed to him the following concept. I said, okay, so you have nerves. We take a muscle from the leg here, a new fresh muscle. We implant it into the arm, meaning the nerves will get new muscle to reinnervate, and the muscle is then again a translator and an amplifier of neural information. You got that? And we have a derotation osteotomy, and then we sit the patient down and we tell him, think of hand movement. We don't know what he needs to think of because we don't know what nerves regenerated. So we sit him down in front of a computer screen, and then he thinks of whatever movement he can think of. And suddenly, after about 6 months, he calls me and says, Doctor, I finally found out what I need to think of. It was thumb flexion. So when he thinks of thumb flexion, there is an EMG signal coming. And then we proceeded. So here we have another patient, but with a similar concept. So here we have the EMG, and then there is the EMG signals on screen, and that is being translated into hand movement as it is. And so then the patients can learn. And then we have a hybrid hand, and this is again the patient you've seen before, meaning there's a hand on top of the hand, just to make sure that the patient has understood with that he can move things around. You remember at the video before, he couldn't lift up the small wooden box. Here he can move a baseball. Some patients are not satisfied with that experience. They say, well, it may work in the laboratory, but will it work at home? So here we have a guy from Italy. He has 1, 2, 3 hands. And with the third hand, he's pushing the shovel, just to make sure that the hand will work also in his home environment. So then we amputate the hand, and then he has the prosthetic hand fitted. And this is, it's called the Michelangelo hand from the company Otto Bock. It has many degrees of freedom. And you can see he can even get these grapes off without squeezing them. So I think this is pretty good hand function, even from a hand surgeon's point of view. This is the last part of that part of my talk, and I think I'm almost done. So we started to experiment about 4 years ago with patients after brain stroke. And because these are our most difficult patients to rehabilitate hand function. And so we do cognitive nerve transfers, and I'll show you this video so you can get an idea what that means. We take nerves that we know the patient can address. So even though if you have a patient that cannot extend the fingers, but you can extend the elbow, we reroute these nerves into the nerve that governs the hand. Can you see the difference? The same nerve, but it's a different function. So we can do nerve transfers so the patient can address this function with that nerve. So it's pretty much the same concept, but different level. And so here again, we have a patient that with a brain stroke, no hand function whatsoever, and then we do nerve transfers. Then he can elicit a signal here, and this is information again the machine understands. He can still flex the elbow, and then we mount a prosthetic device with 3 degrees of freedom only. Now, anybody of you knows patients who had a brain stroke and they cannot move their fingers, and then you see this video and you can see the patient can extend the wrist, they can rotate the arm. So I think it's a good way to reconstruct hands with whatever type of defect you would have. And so so this is a large portion of the patients that we see now in our clinic that come to us with the hope to have hand function restored with that type of nerve transfers. So this comes to the final part of my talk, basically defining limits. How much body is necessary and how much machine can we tolerate? I think this is a very important question, especially today after the COVID crisis, and we have basically virtualized lots of our world. And that brings us to the concept of transhumanism. Can we indeed improve or replace bodily competence or incompetence, bodily incompetence, with the application of technological means? Can we merge the biological matrix with technological systems, not just simply as tools, but in fact to transubstantiate, directly connect to these with our senses and the peripheral nervous system? Is a true embodiment through a technological artifact possible? Now, you remember at the very beginning of my talk, what did I talk about? I talked about cells, and I talked about the fact that we have 10 to the power of 14 cells that we are, meaning that in the end, I think it's an impossibility to think that we can translate biological information into a machine to the point where we can feel at home in it. See? So this is Ray Kurzweil. Who knows Ray Kurzweil? One hand only, amazing, 2 hands maybe. So Ray Kurzweil, he was the chief technological officer of Google for many years. You remember the Kurzweil synthesizers? No? With Stevie Wonder in the 70s, he developed the synthesizers. So he is a very smart man. And so he wrote a book which was called, about 7, 8 years ago, it was called, Will We Live Long Enough to Live Forever? And the idea was that in 2045, the capacity of the modern computers will be such that we can basically download ourselves into a computer, like Matrix, you remember the movie? So it is, it's a surrogate, it's a correlate. It's basically the idea that the human body or the human being or the anthropological idea of how we are or who we are can be translated into a surrogate, into something that is not human in a sense or biological. Merging gadgets with the technological advancements. So the title of the talk is called Cyborgs Ahead with a question mark. Is that a scenario that we can think of? Now Elon Musk has been in the newspapers a lot in the recent weeks. He has finally received FDA approval. You will not believe it. He got FDA approval for an implant going into the brain so we can download our smart apps into our brain. You remember what I showed you before about the muscle being a translator of information? I said there is an impedance of complexity. Now, to even think that memory or any type of biological expression can be downloaded or translated into a binary code is nonsense. So he says, for example, that we can enhance our memory with these implants. Now, Eric Kandel is part of our university in some way or form. What was his big contribution? What is memory? Memory is a synthesis of protein. It's dependent on the entire machinery of a cell doing its work. It's not a binary code. So so there is recently in Standard, there was an article on him, and he said, we will not survive without becoming superhuman. So that's a quote from Elon Musk, saying that we need to get into the machines, and the machine needs to become part of us. So I think transhumanism is a modern form of neo-Gnosticism, meaning that the concept of mind uploading or downloading or all these things basically is a dualistic conception of man. The phantasm of merging man's essence, spirit or soul with modern forms of technology is the expression of a subversive contempt of life and the body of man. What I'm saying is that to say that we're able to find our home in a machine in whatever form that would mean that we could separate the body from the spirit in a way, or that we can transubstantiate in a machine, which I think is a dystopia. So I can highly recommend this book from Thomas Fuchs. He is the professor of Karl Jaspers in Heidelberg of philosophy, and also is the chief of psychiatry. It's called In the Defense of the Human Being. It just came out a few years ago, 2 years ago. So here we go back to a human being that lost both arms and both legs. So if you look at this, so the question was how much machine can we tolerate and how much body can we manage? So here he has 3 children. He is a father so he has a wife. And so before I go to the next image, I'll show you this short video. It's a video where he's a rubber hand that's being brushed and the index finger is being brushed by the same patient. And then suddenly the rubber hand is Sorry. I show this video because I'll show it again so you can appreciate it without the noise, because of its importance to bring to the attention that really we are in the human body because we feel it, because we're in it. Now, even though if I would transplant a hand from a dead body, meaning like Theo Keltz, 21 years old, why does he say that it is his body? Why does he say it's me? It's because his own nerves have grown into the hand. Why does anybody ever would feel himself at home in whatever because he says, I feel that. So he feels in home in that piece of rubber because it's being stroked at the same time from the experimentator. So this is how the woman or his wife interacts with her husband. It's not touching his prosthetic devices, and it's not stroking his knee or whatever because he doesn't have a knee, but he's hugging him, whoever is left. It's an important point to say with a transhumanistic perspective in mind. So machines are like this saying, we control, but the body we inhabit. So I was 1 cell big 57 years ago. Today I'm 10 to the power of 14 cells tall or big or whatever you would call that. But I'm at home in every single one of them. So if my wife hugs me, she hugs me as being the human being that I represent. So she would never, if I would lose my arm and I would have a mechatronic arm, as complex as it would never be me. It's a help, it's a gadget, it's a tool, it's an artifact. So the 46 chromosomes have become flesh in whatever we are. You remember, I want you to leave this door being appreciative of the body you have, so I hope I'm leading to that. Through this body, we express ourselves, we permeate it, and it permeates us. We are a living soul. This body serves us and others, not as avatars, tangible, sensible, now very important, vulnerable, and transient. Meaning the fact that we know that we're going to die lends importance to the fact that we live today. I said to Giulio before, we talked about the immenseness of our memory. There was recently an article from one of the students of Eric Kandel, and he said, forgetting is at least as important as remembering. Because if I would remember everything that happened to me, I would go crazy. So it's important to forget as well. So meaning vulnerable and transience are as important as the fact that we can do things. Transient bodies. Now, you would think you would have an artificial body that could be reset at any point in time. Now, how do we teach our kids ethics? So when you punch the other guy in the eye, the guy realizes it's painful. Now, would he realize it's painful when his own body hasn't been touched or hurt? So even the most simple lessons that we teach our children are respecting the fact that their bodies are vulnerable. And the same is with us. So I think it's an important thing. Now I have 3 slides that are, I think, of importance also with regards to the importance of high quality real life social interactions that was just published now in Nature Scientific Reports. No corresponding effect was found between online social interactions and well-being. It can be concluded that increased online social interactions may not compensate for the absence. I have 3 children, and I tell them the fact that you have Snapchat and whatever these platforms are called does not replace real-life interactions that we have. And I think that's an important thing to know. The next thing is that the fact that we can translate our bodies into virtual realities is also an important fact to know. Mounting evidence has demonstrated that embodied virtual reality during physical bodies are replaced or exchanged in surrogates can strongly alter cognition and behavior. So which means that in the future, we can create our own avatar, that in the metaverse, that from Zuckerberg, we can have our small mini-me's, if you will. It will change eventually the way we relate to our own physical, real body that we have. Now, and this is the last one. I think this is also very important, especially in the context of the COVID crisis. The VR, virtual reality porn platforms are the quickest growing business in this industry. It's unbelievable. So today you can choose an avatar, you can have your VR glasses on, and you can change or you can be in a world that is there. And it's a huge business, and we've just read that, It can strongly alter cognition and behavior. So I think it comes to the fact, in the end, these are questions for the reflection already. How will we integrate the metaverse and all virtual communication platforms for healthy future relationships? I think we've all realized that it's important to have that. I think probably maybe a third of my medical interactions with other professionals has exchanged into virtual platforms. I think we all profit from that. But we need to be careful as to how we use these tools and how we integrate these into a modern society. The question, very fundamental, and we will not answer that obviously, is man a complex machine? So is it that we are biological machines? Yeah, I'm sure you've read the book from Yuval Harari, Homo Deus. So he proposes that. He says man is a complex machine, which I would strongly argue not to be true. Can the human body be replaced by an avatar, cyborg, matrix, upload? Have anybody seen the movie with Johnny Depp, Transcendence? Yeah, there's one nodding. Two. You should see these movies. They are reflecting the way we as a society are approaching these issues. It's a very good movie with Johnny Depp where he's being downloaded into a computer and all the consequences thereof. To what extent is the body with its vulnerability, unique with limitations and transience, not the basis of a learning and relationality? If you've seen the movie Avatar in James Cameron, what is the end of the movie? In the end of the movie, the guy who is in the Avatar, what is he willing to sacrifice? He's willing to sacrifice his own life to be part of the world that they're in. That is the hidden message of it. Meaning that in the end, we want to be where life happens. And I think the most important one, and this is also the final statement here, this is from Steven Spielberg, Ready Player One. Who has seen that movie? 2018. So there's more of that.
I read the book.
Okay, you read the book. So this is, I think, you see in the end scene. So you know the book. Maybe for those who don't know, it's a guy who has VR capacities and he lives in a virtual world. And he finally discovers another avatar, and he kind of falls in love with him, her, whatever. And then he realizes who is behind this avatar. And then he sits on a couch with her, and he kisses her. This is the end of the movie. And he says, this body is the only reality we have. Meaning that in the end, the body we have is the only thing that we really have to interact with other people. And as much as avatars and virtual reality and modern communication are a help to us, I think it all only draws, for me, to the fact that this is to be appreciated. Thank you.
Dear Oskar, here are some real flowers.
Okay, thank you.
You can smell them, touch them.
Thank you. That reminds me of our summer lecture from our rector. He said, "It's me, your rector, in flesh and blood." I like that. Thank you.
I think there is some paper that you can. Thank you very much. We are shocked. We are shaken. We are stirred. We are everything, and we need to recover a little bit before we formulate some sensible question. Unless somebody has already questioned. Barbara, and then Misha Weismuth, and then Rob.
Thank you so much. This was hugely informative. Could you comment on the possibility that you mentioned in your third part of your talk of connecting the nerves directly to the bionic parts rather than having this intermediate step of the muscle device?
So nerve-machine interfacing, that's what you're referring to, has been tried many times in many forms. So with longitudinal implants, with transverse implants. The problem is that when you think of a nerve, you remember this image where I said it's 80,000 nerves in a peripheral nerve, that the voltage you have and the amplitudes you get are so small, and the background noise that you harvest when you put an electrode in there are so big that you cannot differentiate noise ratio from nonsense. So it's not possible to get information out of a peripheral nerve. The other end is the brain itself, brain-machine interfacing. So that has been tried as well, and that is something that obviously also Elon Musk tries to do. The problem is in regards to neuromuscular control, that the way we think of movements is not precise enough at this level so that the machine can understand that type of signal. So that's why we use the muscle as a translator, because when the patient thinks or the individual thinks of a certain movement, the muscle already deciphers that type of movement. Yeah.
Important question. Misha, yeah, the microphone is coming because we're taping it.
To follow up on this question, is this, in your opinion, just a technical limitation?
To pick up information from a nerve?
From a nerve? Or is it just because the, signal to noise ratio will always be too low?
Yeah.
As the first part of the question. And the second part of the question is, you mentioned very much, and also showed this at the beginning with your robots, that how important proprioception is. And so I was curious to know how proprioception of these artificial hands, how does that work, or is it just only visual control?
Yeah. So the first question, it is noise to ratio is a big problem, but it's also a problem of understanding the language. We cannot decipher because, as you know, nerves are being modulated by frequency and the amplitude. So we cannot understand the language of the nerve as it is. So it's a difficulty of complexity of language, and it's also a difficulty of picking up or deciphering noise from meaningful messages. Now, the third limitation, I think, is probably the most important, is that when you go into a nerve, like you have some a nerve pickup electrode, when you pass through the perineurium, it will make a scar, and the scar eventually will make an impedance problem that you cannot understand that at all. Yeah. And finally, also, so I'm a nerve surgeon, so I see lots of patients from the different wards, and if there is a small piece of metal within the nerve, it's extremely painful. So it's also a clinical problem. The second question was proprioception. So we had a long discussion today in my office in regards to proprioception. So in school we learn it's the Golgi, it's the Ruffini, it's the intramuscular afferents. There's a very simple experiment by a hand surgeon in the 80s. It's published in Brain. He has done flexing the PIP joint and the patient who has numbed the median nerve, and he tried to flex the PIP joint, just having it from the extrinsic muscles. And the fact that he numbed the piece of skin around the joint made it impossible for the patient to realize what he was doing. The other example, that's what we were discussing today, the facial nerve is the only nerve in the human body that has or the facial musculature that has no proprioceptive capacities. And the way we control our facial muscles, which are minute distances that we cover, I mean, it's just millimeters of skin that we smile or we can wink an eye, is because the skin that overlies the muscle. That is true for the hands as well as for the face, for example. So the proprioceptive capacities that we have are being transmitted for the most part through the skin overlying the joint. In regards to patients who have a prosthetic device, yes, in the very beginning they need to see and look, but with time the perception that they get from the prosthetic device that's mounted on the remaining arm, they get from that. They listen to the motors, they hear the servos crank the torque, and so that's how they perceive that. I say it's very similar to sitting in a car and shifting from the second to third, or first to second. When do you shift? Do you shift when you see the speedometer going up? No. You shift when you hear the motor crank, and you shift when you hear the butt vibrating the car. So we call that secondary perception. So that's how. Today we have seen a woman where we have done an osseointegration for a thumb. So she's lost a thumb, a young lady. And so then the question was raised by Professor Twinde, how does she feel the thumb? Because she doesn't have any sensation in the thumb. And the woman answered, I feel it because of the remaining thumb present and the bone that sticks there. So it's secondary perception that they work with. Yeah.
Rob.
Thanks, very good talk.
Thank you.
Two-part related question. So the first thing is, you showed so far the aim is to get back to normal functioning, but could you adapt it to have superhuman functioning in a sense that maybe the wrist can keep turning 360 degrees and that's easier to screw a cork?
Yeah.
And this
So So body enhancement, is that what you are getting at? You know, is how can we enhance the gadget so it can be more powerful than my own hand?
And would the brain adapt? Or
Adapt
not?
to that, yeah. All right, so let's just, for example, any type of fingertip that you may have, if a fly sits on there, that's 1/10 of a gram of displacement of your fingertip. You can notice it. If you would have a weight of 10 kilos or 5 kilos, you could still manage to realize what's the weight difference. If you would feel more that you would feel, or hear more that you would hear, you would get into, for example, if ear, if I do just this, I hear it. It's minimal displacement of thermal energy that I can perceive. If I would hear more than that, then I would probably hear Brown's molecular movements. You know, is that a sensible perception? Yes, I can organize a hand that is stronger, that can crush a bottle of water, but then I would do it on the downside that I would not be able to manipulate very gentle movements. So I can do one on what you call it on the and I need to pay on the other side. If I have a night vision glass, you know, I can see the thermal energy of the animals in the wood, but if suddenly there would be a bright light shining, I would go blind. See what I'm saying? So yes, I can make an enhancement, but always auf Kosten, wie sagt man? Yes, and it's a bad trade-off, really. I think the organs we have, the sensory capacities that the human being has, is adapted to the physical-chemical environment that we're in. And any change there would lead to deleterious effects on the other end. And yes, we can adapt to that.
Okay, so there was a problem here with our sensory capacity because the air conditioning was off, and I'm just wondering why in this building often Giulio is the only one who connects perception to action. Why the locals, right? I mean, don't you feel it's 27 degrees?
Yeah,
the thing goes off.
I
Anyway,
noticed it.
So first there is Alexander Cristiani, and then I thought there was Varun Sharma. And then keep your answers a little bit shorter, perhaps, because then we can cover more people.
Yeah, sure.
A very brief question of a more general nature. How does artificial intelligence, in the sense of machine learning engineering, relate to your topic?
Yeah. So we have, I think you need to. So machine learning is an important topic. If you've seen, for example, the last video of the mechatronic hand that was moving, that was a pattern recognition algorithm. So for example, we have here 6 electrodes mounted around the forearm, and we ask the patient to do certain tasks, making a fist, opening the hand, doing whatever kind of movement. And then the algorithm is picking up the different EMG activities and then correlating it to the movement that the patient intends to do. So this is a machine learning that is ongoing, and we need to test or train the system at the very beginning, and then once it's understood, then the artificial intelligence takes over. The big problem with artificial intelligence in voluntary movement is that we do not want to take over the patient's will. And it is very similar if you have a car, you know, artificial intelligence will drive the car, but it still needs to be open to the input of the driver. If the KI takes over, then you have an accident. Then the question is, who's at fault? Is it the KI or is it the patient that drives the device?
Important question. Varun.
Thank you for the mind-extending talk. So I've been fascinated by self-organizing systems in the context of the Bayesian brain from Carl Friston, who describes statistical conditioning between
Can you speak a bit closer to the microphone, perhaps?
Is this better? A statistical conditioning between the external environment and the internal environment, separated by a Markov blanket of sensory stimuli and action effector molecules. And this comes from the cell to the body, to the world, to the universe, potentially. And in the argument that you make about dystopian transhumanist, could you potentially say that augmentation is changing or augmenting the Markov blanket or the statistical conditioning between the external environment and the internal environment? So a person, their ability to interact with the external world changes as you augment with VR or with a different hand or whatever. So that line between when you've augmented far enough to become transhumanist versus a simple augmentation? Do you have a perspective on when you pass that line where you're now more robot than you are a human?
Well, I wouldn't know how to answer that question. In the end, the patients that come to us, they have a real loss. They have a loss of hand movement or hand function. We provide a certain replacement. In the end, if you would ask them, would they rather have their own hand back, meaning their original biological hand, or would they rather live with their mechatronic hand as good as it is? They would always tell you they would rather have the biological hand, because this is my conviction, is the best we can do for the patient. So we're not trying to enhance, because transhumanism in the end is an idea that we are going beyond the body. It's not just replacing something that has been damaged and replacing it with something that's kind of working, but it's going beyond that. And I think we're far away from beyond, and we're not even at replacing it in the same complexity. Yeah.
But would it be immoral if you would build in a handy, a smartphone, a light, a heater, a laser pointer? I mean, would it be?
No, but this is a good.
Professors need a laser pointer.
This is a good question. So, for example, we are currently working on a glove. So one thing that is very important for surgeons is to have an immediate information about certain, for example, blood vessels that are still patent or not. And so we're working on a glove that has an ultrasound embedded, and it will transmit the information of the ultrasound to wireless, to a machine. So then when I have the glove on, I can go inside and I can tell, the blood vessels are working or not. So this would be a real enhancement, because with my finger I cannot do that. I can maybe feel it pulsating, but I cannot hear the patency of it. So that would be a good thing to do.
Okay.
Which we do.
Oskar, move to this side, because we only have 2 more questions. The rest will be asked with drinks and beautiful things to eat. First, Ben.
Thank you for this wonderful talk. I have a question regarding the notion of phantom pain. So when people who lost limbs still feel them in some way. So the patients of yours that get bionic reconstruction, does it go away? Does it kind of merge with the new reconstruct or with the new bionic limb, or is it something that they still feel as alien to themselves?
So that's an excellent question. That's something. Today we have seen a patient like this. You should have come to our outpatient clinic. So the question is when patients lose their arm, you remember 30% of the brain's activity related to the hand. If the hand's gone, the brain is craving for this deafness, because there's lots of information lost. So yes, when we do a bionic reconstruction, the pain levels go down, and the more we are able to do an immersive reality, so meaning that that part is being part of their body, it's an embodiment, the more that pain goes away. So for us, this is also a way for pain treatment. And there is a paper that came out in Lancet about 4 or 5 years ago that just addresses that particular question. So it's a great question.
Okay, and the last question comes from Ginny.
You were talking about the importance of the sense of touch. Would the next step be to have something like a skin transplant, if you will, a skin glove that would replace the sense?
When we wrote up the ERC grant, that was part of our original draft, and we took it out because we realized it's not possible. Now, when you think, I've mentioned it before, 5,000 mechanoreceptors in 1 square centimeter of skin. It's an impossibility. Now, when you think of perception, the fact that you can grade over your skin tap, or you can have braille reading, is dependent on a spatio-temporal distribution of mechanoreceptors. It's not just a mechanoreceptor, but it's the connectivity of that to your brain. And if that is disrupted, it is impossible. Just to give you one example, if a patient comes and tries to commit suicide and he slices his wrists and it's not working, but the nerve is disrupted. And then we suture the nerve, and then it takes about a year for these nerves to grow back into their fingers. For more than a year, these patients have tremendous pain in their fingers because the brain cannot accept the reality that's being presented by their fingers. So just to say that the fact that even within the biological system, it's almost impossible to restore that, it is an impossibility with a sensory glove, let's just say. So that's why we're trying to solve that problem within the biological framework. And I think it's a much better way of dealing with that.
We will need to invite you back in 5 years because the way the things are moving, I think it's going to be fantastically interesting. And now, I wouldn't say the better part of the program because this was fantastic, but the second good part of the program starts, which is great food on the terrace before the storm sets in. So thank you very much.